All right. Today we're going to talk about something called implicit differentiation. What if I asked you to take the derivative of this guy right here? Yeah?
I would probably put it into y plus mx plus b, and then do.
So you would solve for y.
Yes.
You would solve for y and take the derivative from there. What about that one?
Get y along.
How?
I get epsilon, find the inverse, and then do the derivative.
You're really going for it.
What if I got that?
The inverse doesn't exist on this one because it doesn't pass the horizontal line. So while I really love your creativity, you're going to hit a roadblock. Okay? Also, if we were to go up here and we were going to solve, you would get y equals plus or minus the square root of 25 minus x squared. So we don't even have one equation, we have two. And I feel like that would also make our derivative quite complicated. What do you think? Okay. So, I mean, we have some ideas, but they're going to be pretty ugly, right? Okay? Or, like down here, solving for y is going to be next to impossible, okay? These are what we call implicit equations, okay? This is what we would call an explicit equation because we have y written as an equation of x, okay? Down here, we have an implicit equation because we have y sprinkled throughout our equation and we aren't solved for y, okay? So when, and this is all we've been working with, when we have an explicit equation, we take dy dx like that. We have nothing that we need to do up front, okay? If we have an implicit equation, sometimes, yes, we can solve for y. Sometimes it's not going to be helpful to solve for y. So what we need is a strategy in order to be able to take an implicit equation and take the derivative without having to do any algebra up front, okay? And that's what we're going to work on today, all right? So let's think about a couple things. What if I asked you to take the derivative of x squared? You would tell me what? 2x. Okay? Now, this was good because this matched this. Right? Okay. Now, what happens when I say take the derivative with respect to x of y? What do you tell me? You tell me dy dx. Okay. Let's talk about this. What if I asked you for the derivative of y cubed? Let's not get too crazy. What's the derivative of y cubed? Just in general. Let's not even talk about the dx. Okay, you would say 3y squared. Well, I'm wanting you to take the derivative with respect to x. Okay? Well, since this is not an x, we have to go further with the chain rule. Okay? So we have y cubed. We took the derivative of y cubed, but inside of the cubed is y. And the derivative of y with respect to x is dy dx. Okay? Anytime we are taking a derivative with respect to x and our variable is not x, we have to do the chain rule that one step further. Okay? we don't have to do it here because we get dx. Well, that's just one that doesn't need to be written. Okay, but here when we apply the chain rule that one step further, we have dy dx. When our variable does not match what we're taking the derivative with respect to, we have to account for that chain rule in our derivative. Okay, and that is really the big deal of implicit derivatives. Okay, so this is what's going to happen. Okay, when you have an implicit equation, I am going to ask you to differentiate both sides with respect to x. Just one term at a time, you are going to take the derivative with respect to x. Okay? You could have some products, you could have some quotients, you could have some simple power rules, you could have some trigonometric. Okay? Now, you might have more than one term with a dy dx. And since you may have more than one term with a dy dx, I'm going to ask that you get all of your terms with the dy dx on one side and move all of the ones without a dy dx to the other side. Okay? Write it down, and when we do an example, okay, I'll kind of come back to what I mean. And by the end of this, we want dy dx equals. Okay. So you may have to factor out some dy dx's in order to be able to solve for it. Okay. And I'm going to show you what this looks like in an example. So I don't want you to panic right now. This is actually a really nice strategy for derivatives. Again, it gives us a break from all of the intense algebra we've been doing. This is also something that's going to lead us into our first example of a free response question tomorrow. Okay, your AP test is split up into multiple choice, we've seen quite a bit of that, and free response questions. We get to see our first free response question tomorrow. Cool. You're paying attention. Don't know why that happened. Okay, so before we get to our example, okay, if we have something like this down here, we're going to take the derivative of this, and the derivative of this, and the derivative of this, and the derivative of this. And then we're going to see where do we have dy dx's, where do we not have dy dx's, and kind of sort it out from there. Okay? Did you get everything written down that you need to? I don't know, was that a thumbs up? Are you sure?
Yeah.
Okay. This is our first example. Anytime you take the derivative with respect to x, and you don't have an x, then you need to apply the chain rule with d whatever dx. Okay? In this case, it's going to be y. So anytime you take the derivative of y, we also need to account for the chain rule with dy dx. Okay? So here's our first go. So here's this. Y cubed. What's the derivative of y cubed?
3x.
3y squared, but since we're taking the derivative with respect to x, we need to go one step further with the chain rule, dy dx. So 3y squared times dy dx. Plus xy, what do we have going on? A product. We still need to be able to recognize that. So we have a product. The derivative of x is 1 times our second function plus x times the derivative of our second. So what's the derivative of y? 1 dy dx. Okay. Anytime we take a derivative of something that's not x, we have to do the chain rule. In this case, dy dx. And then over here, what's the derivative of 3x plus 1? Allie, do you have a question?
I don't understand why there's dy dx in the equation. I thought that was just a way to say we're taking the derivative before the equation. Why is it
Okay. Okay, so when we had those, what did our equations look like? They looked like y equals blah, 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 right? So let's come back to here, to this right here. If I asked you for this derivative, you would write dy dx equals 9x squared minus 4, right? That's because the derivative of y is dy dx. Do you agree? Okay, I'm trying to.
I can accept it. I just don't really get why that is.
Okay, well we have a lot of notations that we use, right? We use y prime, we use f prime of x, we use dy dx. All of those represent the derivative of y with respect to x. So that's what this is saying. The derivative of y with respect to x. Okay? And so since we have a y here, when we take the derivative, we write this. Okay? Let's see. Was it over here? Okay? When we take the derivative with respect to x, it's never been a problem because everything's been in x. But when we're taking the derivative with respect to x and we have a y, we have to write dy dx because that means the derivative of y with respect to x. Okay. You're still iffy about it.
It's fine. I can do it.
Okay.
I just don't like it.
You don't like it. Okay. We'll come back and talk about it. Okay. Yes.
So, oh wait.
Okay.
Wait, so you only need the dy dx when your derivative has a non-x.
Yes. So if I threw a z in there, you would need dz dx. Mm-hmm. Okay, so right now we have 3y squared dy dx plus y plus x dy dx equals 3, okay? And in order to be able to just get dy dx equals, that's what we're used to, right? We need any term that has a dy dx on one side and any term without a dy dx on the other side. Okay? It doesn't matter which side you choose, but I'm probably more likely to keep my dy dx's on the left, just because we like our equations to look like that when we get down to the solution. So I'm going to keep 3y squared dy dx plus x dy dx on the left, and then I'm going to subtract that y over to the right side. So we have 3 minus y on the right side. Now, on the left side, I have two terms. They both have dy dx in them. So what we can do is we can factor out that dy dx. dy dx is being multiplied to what I have in parentheses. So to get dy dx by itself, we can divide it over. Mhm. Since we have an implicit equation involving x's and y's, our derivative will also involve x's and y's.
Yeah.
What questions can I answer about what we did up here? Yes.
Can we expect to see like polynomials be turned into rational?
Okay. Yes. When we have an implicit derivative, it's a pretty good chance you're going to have a fraction for a derivative. Yes. Since we have multiple terms involving dy dx, that almost like forces it to be a fraction. So what we're going to see tomorrow. Tomorrow we're going to look at our first free response question, where we're going to actually get a horizontal and vertical tangent line from this. Not going to worry about that right now. So that is where we're going with this, because oftentimes we have them as fractions. Okay. Anything else about this process before we look at another one? My biggest concern in these problems is you recognizing a product rule and you remembering that the derivative of a constant is 0. Those are the two things that I see forgotten the most. Okay. Now, I want to talk about a couple things. xy equals 1. Is that the same thing as y equals 1 over x? Yes. Okay. So, if we had y equals 1 over x, we like to think of that as y equals x to the negative 1, right? And dy dx, the derivative of y with respect to x, would be negative 1 x to the negative second power. Do you agree? Okay. Now, if we looked at this as an implicit equation, okay, in this case it is a function, okay, let's talk about our process if we look at it this way. Well, right here we have a product, right? So we have the derivative of x times y plus x times the derivative of y equals, what's the derivative of the right side? Okay, so we have x times dy dx equals negative y, and our derivative would be negative y over x. Okay, now those two look different when we get down to the derivative. Okay, the main reason is because this is with x's and y's, and this one is exclusively x. Okay, or explicitly x. Okay, this is an explicit function. Our derivatives are only going to have x in them. We've kept this implicit, so we have to work with the x's and y's in our derivative, which means our answer will involve both. Yes.
If it is implicit, then should we always do implicit?
I have no problem with you taking xy equals 1 and rewriting it like this for the derivative, but more than likely, if I give you an implicit equation, it's not going to be able to be rewritten, okay? Or there's very, very few that would be able to, okay? Most of the time, they have quite a few terms, like the one that we just saw. Okay. If you're taking the derivative. Okay, and we have an implicit function. If you are differentiating with respect to x, and you do not have an x, then you need to take the chain rule and multiply whatever derivative by, in this case I used a star, d star dx. If it's in y, you have to multiply that derivative by dy dx. If it's a z, you have to multiply it by dz dx. If it's a star, you have to say d star dx. Okay? If we're differentiating with respect to x, and x is not one of our variables, we have to use the chain rule and account for the derivative of that non-x variable with respect to x. Yes?
If there's like two non-x variables, would it be like dy, z?
Okay, so if we had, I think this is what you're asking, if we had like x, like 2x squared plus 2y squared plus 2z squared, can I do that? Like, you mean like there's more than one variable?
Kind of. I
Okay.
meant like at once. Like if there's like a 2cxy, or will that not happen?
So when we get into the applications of derivatives in Unit 3, it is possible that we have more than one variable in there. So, like in this case, if I'm taking the derivative with respect to x, then we could write this as 4x. We would have to write this as 4y dy dx. And we would have to write this as 4z dz dx. Is that answering your question?
It does like clarify something, but like I guess my question is like, will there ever be like a y and a z right by?
There could be.
So would you write that as like d y z?
If you had y z, you would write dy dx times z plus y times dz dx, because it would be a product, and we would have to use the product rule, and we would just notate that we were taking the derivative of y with respect to x. We were taking the derivative of z with respect to x. Is that clarify?
Yes.
So let's do this. I eventually want to find the slope at -1, 2, but I don't want to worry about that right this second. If I'm asking you to identify a slope, then what is the first thing we need? We need a derivative. So I'm going to give you 2 minutes to work through what you think this derivative is. Okay, and then stop. Stop when you get to the derivative. Okay, compare your process as you go with the people that you sit next to. Okay. Your first step looks like my first step. Your first step looked like my first step.
Yeah.
Oh, you forgot to keep it in. And you forgot to include. So this should be a negative x instead of a plus 1. Okay, so you can do this a couple different ways. You can either subtract the quantity of the product rule, or you can think of this as like a minus x times y, which is kind of what I did here to avoid the parentheses. Okay, do you have any questions about any of those terms up there? Is everyone okay with 0 on the right side? I know it seems silly, but one of the most common errors is if there's a constant over here, we like to carry it down in the derivative. I don't know why, but that's just something I see a lot of. So if you kept dy dx on the left side, you would have moved y minus 2x to the other side. We could factor out dy dx, and I would probably write this as 2y minus x because I like to write a subtraction instead of a negative value, but y minus 2x over 2y minus x, or something equivalent to that, would be your derivative. I see erasers going. Can you tell me what the hiccup was for you?
I forgot that it was negative y. That's it.
Okay, so then that affected everything else. Okay. Anything else for erasers? And if you write this as negative 2x plus y, that's the same thing. It's fine. Did anybody get 2x minus y over x minus 2y? Like if you get 2x minus y over x minus 2y, these two mean the same thing because it's the opposite numerator and the opposite denominator, so they equal out to be the same. Okay. All right, so what I was really hoping to do with this is evaluate the slope at negative 1, 2. And if we want the slope at negative 1, 2, then we need to take our derivative and plug in the coordinate negative 1, 2. So this is the notation, dy dx, that's the evaluate bar. Okay, so we can plug 2 in for y, negative 1 in for x, to get our slope. What is our slope?
4 over 5.
4 over 5? Kind of a nice slope, right? Okay. What if we wanted to write a tangent line equation? Owen, what would our tangent line equation be?
Y minus 2 equals 4/5 x plus 1.
Do you agree with Owen's tangent line? You hope so.
Well, like if it's anything other than that, then there's something weird going
Okay, no, that is your tangent line. Okay. Tangent lines don't change. The process doesn't change. Our derivative, we're just taking a little bit of a different route. Okay? One more example involving some trig.
Oh, that's disgusting.
It's not so bad. Okay, so is this an implicit function?
No. Yeah. Yes. Oh, I thought you said that. Yes.
I said implicit. It's implicit. You don't want to solve for y. You don't want to solve for y. So, when we take our implicit derivative, what strategy do we need to use within that? Try again. The product rule. So we have the derivative of our first function is 2 cosine of x times our second function, cosine y, plus our first function, 2 sine of x. Yes? What? Yes, do the thing. Times the derivative of our second function would be negative sine of y dy dx. Equals
0.
Good job. Didn't like read that much. Not very smart with it. Okay, so what we have this guy, negative 2 sine x sine y times dy dx equals, I'm going to subtract this over, negative 2 cosine x cosine y. Some of you are getting excited, right? No, I just have an itch. But you're getting excited because you can see where this is going. I don't have a problem if you leave it like this. There is nothing wrong with it. However, if you see that you can reduce it because we have some trig things going on, right? Negative 2 over negative 2 cancels out. What is cosine of x over sine of x? And what is cosine of y over sine of y? There's nothing else you can do. You leave it like that. It does not cotangent squared. It does not cotangent x times y. It's cotangent x times cotangent of y. Okay. Tomorrow we will go over our quizzes. Okay. And then over the next couple days, we're going to talk about, well, I guess not tomorrow. Tomorrow we're going to talk about tangent lines that are vertical and horizontal. And then Wednesday, Thursday, we're talking about exponential and logarithmic derivatives. So we're going to get some more derivative rules Wednesday, Thursday. Okay. Yeah.